Let us solve a few questions which have appeared in GATE Mechanical Engineering from the chapters on strain energy. So the first question is like this. There is a frame of two arms of equal length L, which is shown in the figure. So the frame is like this. There is this is like a simply supported beam, and there is another arm which is perpendicular to it, which is like a cantilever. So this length is L, this length is also L. And assume that it's both the arms have same flexural rigidity, which is EI. There is a force P acting like that here at the end of the horizontal arm. We are supposed to find out the deflection of this, of the point where the force is applied. So how do we solve this problem? Let's say we name them A, B and C. These are the names of the 3 points. So now let's see what is happening, how to solve this one. This is a very, very good problem actually, and it requires a lot of understanding. See, the portion BC is not exactly a cantilever also. It is just something which is supported at B with only translational constraint. It is free to rotate about B. It is not fixed at B. It is only pinned. There is a pin at B. Okay, but because it's rotation, or let's say because the translation at B is not allowed, so the portion AB is giving it the rotational constraint there. So even though the point B is pinned, the rotational constraint is coming from AB. So if I draw the picture of the frame again here with its thickness on, so it is like this actually. It is like this. This is AB and this is BC. It's like this. So at here, this portion of the beam, this portion is providing the rotational constraint to it. So when this bends, it will bend like that, like this, instead of bending like that, like a straight line. It will bend like the beam, like this. So for the portion BC, the strain energy, I'll say UBC is equal to integration 0 to L P into x square px square dx upon twice Ci. It is nothing but m square dx upon twice Ci integration over the whole length, where m at any section in BC will be px, where x is the distance from load. So if I just take this integration, it is 0 to L p square upon x cube by 3. So it becomes 6 EI x cube, and this becomes 0 to L. So this is equal to P square L cube upon 6 EI. So this is the strain energy in BC. For AB, now let's see. At AB, the point B cannot translate down. It can only, it will have a rotation. So it will transfer the moment, but it will not be able to transfer the force. So for AB, there is a constant moment acting which is equal to PL. So for AB, the strain energy is nothing but 0 to L m square dx upon twice Ei. And now m is a constant which is equal to P square L square, or rather PL is the value of m. So m square is P square L square. So it comes out upon twice Ei. And integration of dx is nothing but L. So this value is P square L cube upon 2 EI. So the total strain energy is UBC plus UAB, which is nothing but P square L cube upon twice EI plus P square L cube upon 6 EI. So if I add the two numbers, I get P square L cube upon this becomes 3 by 6 plus 1 4 upon 6 EI. Now we know that this is also equal to u is also equal to 1 upon 2 p into delta. So that is equal to 4 upon 6 is 2 upon 3 p square L cube upon EI. So that gives me delta is equal to, this p gets cancelled out, 2 goes up, 4 upon 3 p L cube upon EI. So that is the answer. So let's see the options which have been provided. Option A is PL cube upon 3EI. Option B is 2PL cube upon 3EI. Option C is PL cube upon EI, and option D is 4 upon 3 PL cube upon EI. Now let's see if we can, without even solving, if we can, eliminate a few options. It makes the life easier. So let's see if we can eliminate a few options. See, the first answer is PL cube upon 3EI. Oh, I'm sorry, this is 3EI. Now, please remember the deflection for a cantilever beam is PL cube upon 3EI. Now, is this a cantilever beam? No, it is not, because it is pinned at point B. So, obviously, this answer is wrong. It cannot be the answer. So, this is a wrong option. Directly, we can eliminate option A. It is not the correct answer. Let's go to option B. Option B is 2 upon 3. This is 2 upon 3. I'm sorry. 2 upon 3 PL cube upon EI. Now, this option may be right. But let's see what is happening at point B. See, had point B been allowed to bend sideways or move sideways, then it would have loaded AB section in bending as well as BC section in bending. Because PL cube upon 3EI plus PL cube upon 3EI is equal to 2 upon 3 PL cube upon EI. Right? It's like two beams bending together, each by PL cube upon 3EI. So this option also seems to be wrong, because the second section doesn't have any translation. Now let's go to third answer, which is PL cube upon EI. Now this we do not know whether it is right or wrong. It may be right or it may be wrong. So we have eliminated successfully two options. We have eliminated option B and we have eliminated option A. So now we have to choose between PL cube upon EI and 4 upon 3 PL cube upon EI. And we know from solution that this is the answer. Now, I'm not saying that we do not solve the problem and try to guess the answer, but if we eliminate a few options, it helps a lot in getting a correct answer fastly. So that's why I'm just telling this technique, that please eliminate options which you feel and which you know rather are not correct. So that reduces the error which is possible, because if you eliminate either one or two options, then obviously the probability of hitting the correct answer is increased. Now let's see what is question number 2. Question number 2 is like this. The strain energy stored in the beam with flexural rigidity EI and loaded as shown in figure is. Now, what is a figure? A figure is that of a simply supported beam. Simply supported beam like this. And its span is 4L, and at the distance of L from both ends. So, at this L, there is a force P at both ends. And this distance is obviously 2L, because the total span is 4L. Now for this case, we are supposed to figure out what is the value of strain energy. So this is a very easy problem actually, if we just apply the principle very easily. Now we know that for this section, let's say I name the sections as A, B, C and D. So for AB and CD, we know that U for either of them is equal to integration from 0 to L, because that's the span is of length L, P square x square dx upon EI. Because the the force is increasing. Now why it is Px? Because each reaction is also P here, because it is evenly distributed, the load is evenly distributed, so the reactions are also equal to the forces, applied forces P and P. So obviously at any section here, M, the bending moment is Px, so hence this is the value of U. So if I just do the integration, I get it is P square, this is P square x square upon twice EI, so it is twice EI, and this is x cube by 3, 0 to L, so that becomes P square L cube upon 6 EI. So this is the strain energy in AB, and this is the strain energy in CD also. So the total strain energy in AB and CD together will be twice of this. Now let's see what is strain energy of BC. For BC, the moment is constant at this level. M is P into L, because it's like moment at P. At point B is the moment in BC also. That's a pure bending. So this is nothing but, it is direct integration M square dx upon twice EI. M is a constant, which is equal to P square L square, or rather PL. So I do this integration, which makes the value P square L square into L upon twice EI. So this is nothing but P square L cube upon 2 EI. So the total strain energy U total is equal to UAB plus UBC plus UCD. This is nothing but P square L cube upon 6 EI plus P square L cube upon 2 EI plus UCD, which is nothing but equal to UAB. So I multiply this by 2. So if I solve this problem, this is 1 upon 3 plus 1 upon 2. This becomes equal to, it becomes equal to, just let me check, becomes equal to this is P square L cube upon EI. This becomes equal to 4 upon 3 into 4 upon 3. So that is the answer. Let me check the calculation once more. So I have AB and CD. So U for AB or CD is 0 to L P square x square dx upon twice EI. So it becomes P square upon 2 Oh no, I've done something wrong here. Sorry, this is 0 to 2L. That's why I was thinking that I'm not getting the right answer. This is 2L because the span length is 2L, so this becomes 2L here. So this is 2. So this gets cancelled. So this is not there. So that is 1 upon 3 plus 1. So that is 4 upon 3, right? So this is the answer. So the options which have been provided are P square L cube upon 3I. Option B is 2P square L cube upon 3EI. Option C is 4 upon 3 P square L cube upon EI. And option D is 8P square L cube upon 3EI. So obviously this is answer C. Now here also we can apply a few simple fundamentals and get the right answer without, we can guess and strike off a few wrong answers. But this problem is easier to solve rather than guess here. So that's why I solved the problem without guessing. And this is the answer. Now let's see question number 3. Question number 3 is like this. The stepped steel shaft shown below is subjected to 10 Newton meter torque. The stepped shaft like this. And there is a torque applied here, which is 10 Newton meter. The diameter of the higher or the bigger diameter step is 15 millimeter, while the smaller step its diameter is 25 millimeter. Both the lengths are 100 millimeters. So this is 100 from here to here and all that. Now we have to find out the strain energy which has been stored in this shaft because of the torque. And the shear modulus is given as 80 GPa. Now let's see, it's very easy problem to solve because there is nothing big deal in this. See, we can take the two shafts separately or two steps separately. There is torque T in this. So for this U, let's say 1 is equal to T square L upon 2G into J. J1 I'll put and L1. Now T is equal for both of them because it's a parallel shaft. So sorry, they are in series. So the load is transferred equally. So both of them are loaded with T. So now in this case, because L is also same, I'll just put L1 and L2 equal to L, which is 100. So in this case, U1 is this much. Now similarly, U2 is T square L2 upon 2G J2. Now total U is nothing but T square L1 upon 2G J1 plus T square L2 upon 2G J2, which is nothing but T square L upon 2G 1 by J1 plus 1 upon J2. Now this is the torque in both of them is 10, so the square of that is 100, multiplied by length is 0.1, divided by 2 into 80 10 to the power 9, that's in GPa. Now J, the value of polar moment of inertia for the shaft or for a circular area of cross section is pi d to the power 4 upon 32. So this becomes 1 upon pi into, this is 50, so 50 in meter will be 0.05 to the power 4 by 32 plus the other one is pi into I write it here again, 1 upon pi into 0.025 because its diameter is 25 to the power 4 by 32. So if you do this calculation, you will finally get this 32 can be taken as common out, so it becomes 100 into 0.1 is 10 multiplied by 32, which comes common, upon 2 into 80 into 10 to the power 9 into pi is also common, so I take out both of them common, 1 by 0.05 to the power 4 plus 0.025 to the power 4. To do this calculation, you will get the value as 1.73. Actually, you will get 1.73 10 to the power minus 3. But because we are supposed to find out the strain energy in shaft in Newton millimeter, so this value will be there, which is only 1.73. So that's basically a simple numerical problem, and it is heavy on calculation, but it is very easy on the principle. So let's see the options which have been provided. Option A is 4.12. Option B is 3.46. Option C is 1.73. And option D is 0.86. So obviously we know that this is the right answer, 1.73, or option C. So these are the problems which have appeared in GATE, and they are there in the book. But I urge you to please solve as many problems as possible from various books, because strain energy is an important concept, and it is very useful also. And I'm sure there will be at least one question from strain energy principle in GATE, because this forms a very fundamental portion of strength of materials. So please solve a few problems if